In Part 3 of Session 1, we will briefly discuss petrochemical products derived from the hydrocarbons obtained from crude oil.
In fact, almost all key raw materials for a petrochemical complex can be obtained directly or indirectly from crude oil fractions. Typical examples include carbon black, an extremely fine high surface area carbon powder produced by incomplete combustion of heavy petroleum streams, as well as acetylene, methane, ethylene, propylene, butylenes, benzene, toluene, xylene, BTX, naphthalene, often derived from heavier petroleum fractions, and coke. Natural gas and coal can also serve as sources for some of these chemicals. Historically, coal was a major source of aromatics such as BTX and naphthalene, but today petroleum-derived streams are among the most important precursors in industry. These compounds are intermediates, meaning they are converted into many high-value products. For example, carbon black is widely used as a pigment and as a reinforcing agent in automobile tires, with smaller applications in electromagnetic wave absorption. Acetylene can be converted to vinyl chloride, the monomer for PVC. Several routes produce acrylonitrile, a key building block for polymers and copolymers such as SAN, ABS, commonly used in 3D printing filaments and durable plastic parts, and ASA. Methane is a major feed for methanol, used as a fuel component and an industrial solvent. Ethylene leads to products such as ethanol, ethylene oxide, and ethylbenzene, and it is the foundation for polyethylene, one of the most common plastics in daily life.
Propylene is used to produce isopropyl alcohol and polypropylene, and it is also an important route to acrylonitrile, highlighting the industrial value of that intermediate.
Butane can be converted to butylenes and then to butadiene, a critical feedstock for synthetic rubbers. Maleic anhydride is another important intermediate with applications in coatings, paints, and polymers. Finally, aromatic chemistry is central to petrochemicals. Benzene is converted to ethylbenzene and then styrene, which leads to polystyrene. Benzene also produces phenol, the main raw material for phenolic resins. Toluene can be converted to benzaldehyde and benzoic acid, and xylene is used to produce phthalic anhydride, a precursor to phthalate esters used as plasticizers. Naphthalene, once primarily obtained from coal processing, is also used to produce phthalic anhydride.
As a more detailed example, let us start with methane and review what can be produced from it in industrial chemistry. Under controlled partial oxidation, methane can produce carbon black, which is widely used as a reinforcing filler in automobile tires. Methane is also a major feedstock for hydrogen production in petrochemical plants and refineries through steam methane reforming, SMR, which produces a mixture of hydrogen and carbon monoxide. When additional steam is added and the gas is sent to a water-gas shift reactor, more hydrogen is generated and carbon dioxide becomes the main byproduct. After separating hydrogen from carbon dioxide, hydrogen can be combined with nitrogen from air to produce ammonia via the well-known Haber-Bosch process. Ammonia can then be oxidized to produce nitric acid, and nitric acid can react with ammonia to form ammonium nitrate, an important nitrogen fertilizer that also has controlled industrial applications. Ammonia can also react with carbon dioxide to produce urea, another major nitrogen fertilizer. The hydrogen and carbon dioxide mixture from the shift section can also be routed to a methanol plant, where methanol is produced. Methanol can be used as a fuel component and as an industrial solvent. Methanol can be oxidized to formaldehyde, a key precursor for phenol formaldehyde resins. Methanol can also react to form methyl chloride, an industrial solvent used for removing oils and greases in certain manufacturing operations. Methane can be converted, under controlled conditions, to hydrogen cyanide, a highly toxic intermediate that is handled only in tightly regulated industrial systems. Hydrogen cyanide can be used to produce acrylonitrile, a highly valuable petrochemical intermediate with multiple production routes, highlighting its industrial importance. Methane can also be converted to acetylene, which serves as a building block for several key products. Acetylene can form vinyl chloride, the monomer for PVC, and vinyl acetate, a monomer used to make adhesive polymers. Acetylene can also be converted to chloroprene, which polymerizes to polychloroprene, neoprene, a weather-resistant rubber used in products such as gaskets, seals, tubing, O-rings, and as a base resin in certain adhesives and coatings. Finally, methane can be chlorinated under controlled conditions to produce chloromethanes, including methyl chloride, methylene chloride, chloroform, and carbon tetrachloride, which have important industrial solvent applications.
Next, let us focus on ethylene. Ethylene is not present naturally in crude oil. Instead, it is produced industrially, most commonly by steam cracking of hydrocarbon feedstocks such as ethane, propane, or naphtha. Steam cracking is one of the most important petrochemical processes because it generates light olefins, and ethylene is typically the main product. The largest application of ethylene is the production of polyethylene, one of the most widely used plastics. Ethylene is also a key starting point for several oxygenated chemicals. For example, ethylene can be converted to ethylene oxide by reaction with oxygen under catalytic conditions, typically a few hundred degrees Celsius and elevated pressure. Ethylene oxide is a highly valuable intermediate. Adding water produces ethylene glycol, well known as an antifreeze component and also a major feedstock for polymers. When ethylene oxide reacts with ammonia, it forms ethanamines, which are widely used in liquid detergents, emulsifiers, gas treating, and many specialty formulations. Polymerizing ethylene oxide produces a family of polyglycols used broadly in chemical, pharmaceutical, and biomedical applications. Common examples include diethylene glycol and triethylene glycol, which are also used as intermediates in producing polymers such as polyurethanes. Ethylene oxide can also react with organic alcohols or alkyl phenols to produce glycol ethers, important industrial solvents for dissolving gums, resins, and cellulose esters. Ethylene chemistry also connects to other major industrial pathways. Under certain routes, acrylonitrile can again be produced using ethylene-derived intermediates, which emphasizes how important acrylonitrile is as a commodity chemical with multiple production pathways. Ethylene can also react to form ethylene chlorhydrin, an intermediate used in chemical manufacturing, including pharmaceuticals, biocides, and plasticizers. Another major route is the production of chlorinated solvents. Adding chlorine to ethylene can produce ethylene dichloride, which can then be converted to vinyl chloride, the monomer for PVC. Finally, ethylene plays an indirect but critical role in producing styrene, and therefore polystyrene, by first reacting benzene with ethylene to form ethylbenzene, followed by dehydrogenation to styrene. Ethylene can also be converted to ethanol through hydration, and ethanol can be oxidized to acetaldehyde, which is a building block for several useful resin systems.
Another key petrochemical building block is propylene. Propylene is not present as a major component of crude oil. Instead, it is produced mainly by steam cracking of hydrocarbon feedstocks and by refinery conversion processes that generate light olefins. In petrochemical complexes, propylene is a central intermediate because it leads to a wide range of high-demand products. The largest application of propylene is the production of polypropylene, one of the most widely used polymers, similar in industrial importance to polyethylene. Propylene is also the starting point for isopropyl alcohol, IPA, produced by controlled hydration of propylene. During the global pandemic, IPA demand increased sharply because it is the main active component in many disinfectant formulations. Propylene chemistry is also essential in the detergent industry. By oligomerizing propylene to form a propylene tetramer and then attaching it to a benzene ring, the industry produces dodecyl benzene, which is a key precursor for the surfactants used in laundry detergents. Similar detergent range alkyl benzenes can also be produced using propylene-derived olefin mixtures through related pathways. Propylene can react directly with benzene to form cumene, which is an important intermediate used to manufacture phenol and acetone through the cumene process. Acetone is a widely used solvent, miscible with water, and effective for dissolving many organic materials, including certain paints and coatings. Acetone can also be produced through alternative routes, including oxidation of isopropyl alcohol under controlled conditions. Propylene is further converted into propylene oxide, a major intermediate for producing polyether polyols and other chemical products. In addition, propylene is a key feedstock for producing acrylonitrile via industrial routes that use ammonia, oxygen, and catalysts, again highlighting the strategic importance of acrylonitrile as a commodity chemical. Finally, chlorination of propylene at elevated temperature produces allyl chloride, which is used to manufacture intermediates such as epichlorohydrin and related alcohols. These intermediates can be further converted into glycerol, another important industrial chemical used in many formulations and processes.
Normal butylene and isobutylene are two other important olefins that can be produced through steam cracking of hydrocarbon feedstocks. Hydrating normal butylene produces secondary butyl alcohol, sec-butanol. This alcohol can be used as a solvent, and its ester derivatives are also widely used as solvents and, in some cases, as plasticizers. By dehydrogenation of sec-butanol, we obtain methyl ethyl ketone, or MEK, which is one of the most important solvents in the paint and coatings industry. Another key pathway is the production of butadiene, a precursor for a large family of polymers and copolymers. Polymerizing butadiene produces polybutadiene, BR, a synthetic rubber widely used in tire manufacturing as a replacement or supplement to natural rubber. When butadiene is copolymerized with other monomers such as styrene and acrylonitrile, it produces additional major industrial rubbers and plastics. Now, returning to isobutylene, one important derivative is isobutanol, isobutyl alcohol. Esters of isobutanol are effective solvents, particularly in varnishes and coating formulations. A copolymer of isobutylene and isoprene produces an elastomer with low gas permeability and good resistance to environmental conditions, which is valuable in applications requiring good sealing performance. Finally, dimerization and trimerization of isobutylene produce di- and tri-isobutylene, which are used in rubber-related products and as additives in lubricating oils. Polyisobutylene is another important polymer family, often described as a colorless, tacky, rubber-like material with wide industrial applications.
The final category is aromatic and cyclic chemicals. In this section, we will review key products derived from benzene, toluene, xylene, and cyclohexane. These aromatics are commonly separated from reformate in an aromatics complex. One important pathway is the production of benzene from toluene. As discussed earlier, combining propylene with benzene produces cumene. Under controlled oxidation with air, cumene forms hydroperoxide intermediates that are converted into phenol and acetone. Phenol can also be produced directly from benzene through controlled chlorination and hydrolysis routes. Phenol and acetone are also building blocks for bisphenol, an important monomer for polycarbonates and a key precursor for epoxy resins. In addition, polymerization reactions involving phenol, such as with formaldehyde, urea, or epichlorohydrin, lead to major families of phenolic resins. Another major aromatic pathway is styrene production. Benzene reacts with ethylene to form ethylbenzene, which is then dehydrogenated to styrene. Styrene is the monomer for polystyrene, a widely used industrial polymer family. Benzene can also be converted to dodecylbenzene, an important precursor for surfactants and laundry detergents. From toluene, an important pathway leads to nitrotoluene and then to toluene diisocyanate, TDI, one of the key building blocks for polyurethanes. Xylene is separated into ortho, meta, and paraxylene. Under controlled oxidation, these form important products such as phthalic anhydride, isophthalic acid, and terephthalic acid. Phthalic anhydride is used in plasticizers, dyes, and pharmaceutical intermediates. Isophthalic acid and terephthalic acid are crucial precursors for polyester materials, including PET, widely used in packaging and beverage bottles. Finally, cyclohexane is an important cyclic feedstock.
Its oxidation produces cyclohexanol and cyclohexanone intermediates. These intermediates lead to products such as adipic acid and caprolactam, which are central building blocks for nylon, one of the most important engineering polymers with extensive industrial applications. To summarize Session 1, I hope you now see why crude oil is essential in modern life. We discussed how crude oil forms over millions of years, who the major global producers are, and what crude oil contains. You learned key definitions in hydrocarbon processing, and through several block flow diagrams, you became familiar with the major units in a petroleum refinery. Finally, we introduced the main organic chemicals that can be produced from petroleum and natural gas feedstocks, and how these intermediates connect to the materials and products we use every day.
Thank you very much for watching this session. I hope it helped you build a clear picture of the key concepts and how the major refinery and petrochemical pathways connect together. In the next sessions, we will go step by step through the units in more detail, with simplified diagrams and practical explanations. Please continue with the rest of the sessions. I look forward to learning with you.